from International Computer Science Institute at Berkeley and UC Berkeley. Just by the way of introduction, I met him pretty much almost the first day I landed in this country, because we met at ICSI 1983. And can I give the whole story with Alan, or shouldn't I mention it? It was very interesting. So I'm standing there with my professor, Fujisaki, and with Professor Anna Oppenheim, whom I met in Japan. So there was the second person I guess I knew in US at this time. I'm talking to them. And at a certain point, Alan talks to me and says, and by the way, the person I really hate is Morgan. I turn around, there is this guy with long hair, with a backpack on his back, and it was Morgan. They had some issues. I mean, we don't have to, it wasn't anything serious. But so, and then at this moment, the doors opened and we all went to have a dinner. And we ended up at this big shot table somehow. I mean, all these big shots from DSP were sitting there with Alan Oppenheim and everybody. And two of us, little people. So yeah, there was nothing better to do but to talk to each other. So we talked to each other, and he says, what are you doing here? I said, I'm looking for a job. And I said, what are you doing? He said, I'm looking for people. So we met next day, and for various reasons I didn't end up with Morgan, who was then head of the speech research at National Semiconductors, and I ended up in Santa Barbara, as you know from the last week talk, of course. But we very much stayed in touch and in contact. Morgan really introduced me to neural networks. He started working on that in 1980 when no speech people actually had any idea that such a thing exists. And we pretty much have there ever since, right? And that did, as you can see, we did a number of works together and a number of even interesting works which other people are interested in together. And he's my dear friend and colleague, and here's yours.
Okay, thanks, Ian. Okay, guess I'll get a little amplification. This, hopefully, this will still work. So, I'm going to talk to you today about neural networks speech recognition. Not that many years ago, this would have been a really oddball topic, way out of the mainstream. This is not the case. However, I think there's enough, because of that, there's enough people who are new to the topic that they think that perhaps it was invented 4 or 5 years ago. And in fact, there's been a lot of work for a long time. And so I'm going to try and take you through a sort of historical perspective of the use of neural networks for speech recognition, going from the very basic structures to the piled higher and deeper ones that we have now. Okay, but we're going to start with a little story. So Holmes and Watson, I think probably most of you are familiar with Sherlock Holmes stories, great detective in literature. Holmes and Watson went on a camping trip. So they had a nice meal, they had some wine, and late at night, early in the morning, Holmes nudged Watson and asked, Watson, look up into the sky and tell me, what do you see? Watson says, I see millions of stars. Holmes asks, and what does that tell you? Watson replies, astronomically, it tells me there are millions of galaxies and potentially billions of planets. Astrologically, it tells me that Saturn is in Leo. Theologically, it tells me that God is great and we are small and insignificant. Horologically, it tells me that it's about 3 a.m. Meteorologically, it tells me that we will have a beautiful day tomorrow. What does it tell you, Holmes? Someone stole our tent, you idiot. So there might be a big picture that we're missing in using deep neural networks, but there are some really nice results in a number of application areas, not just speech recognition, but also in speech recognition. And there's lots and lots of enthusiasm. Now, if you've been around a little while, you saw this happening before, but that's not necessarily a bad thing. So we kind of view it as neural networks redux, and this is kind of being the third wave. So the first wave, which I'm actually far too young to have experienced directly, is what happened in the mid-50s to the early 1960s with some things called perceptron learning and Adline systems. And this was what I'd think of as the BS, the basic structure. Then we got multilayer networks. Actually, there were some multilayer networks earlier, which I'll get to. But they became more popular in the mid-'80s to late 1990s with the backpropagation algorithm and multilayer perceptrons, or MLPs. I think of this as the MS. You guys are all involved in the educational process, so you follow this. And now it's the deep networks, which are piled higher and deeper. This is the PhD period. So in the first wave, people did work with digits and some other small vocabulary speech recognition tasks. The second wave, large vocabulary continuous speech recognition, we and others did a bunch of that. And now it's kind of mature use, and it's broadly competitive with other techniques. Proponents would even say better. So starting with early point, automatic speech recognition also had an early start. The best known early paper was a 1952 Bell Labs paper on digits, speech recognition of digits. Although you could say that speech recognition work started with Radio Rex in the 1920s. Our colleague Koenig has several of these. It's a little doggy that sits in a doghouse, and if you say Rex, the dog comes out. And basically, the house resonates and breaks a circuit, and the spring pushes it forward. So it's pretty, primitive speech recognition. In fact, if you make just about any sound with enough energy, the dog comes out. So the first real one probably is this 1952 paper, and this was a digit recognizer. And you could think of it as approximating the energy informant's. It's sort of dividing up high frequencies and low frequencies. High weren't that high, so it's sort of first and second formant. It had some robust ideas to it, insensitive to amplitude variations and some timing variations. And they got it to the point where it worked very well for a single speaker under very, very pristine conditions. But other than those limitations, the main weakness was sort of technological. It was a bunch of resistors and capacitors that had to be tuned and then worked for that person. There was also, if you think of it in terms of what sits on your iPhone right now, this was a picture of the system. So that was to recognize a few digits. It took a lot of space. So ASR history is not the real point of this talk. It's kind of fun to talk about. It's worthy of other talks. But I think the main thing to talk about with that is that we started off with templates of examples of spoken words, and then looking at the distance between them and the new word that you want to classify. This led into a period where the statistical models became very popular. Hidden Markov models are the approach of choice for many years now. This was based on mathematics that was worked out in the late 60s. The biggest source of gains since then have been lots and lots of computing. That's a point that might get some controversy, but I think basically at the least you could say is that the availability of lots of computing and storage has made it possible for people to develop engineering improvements that given us the kind of systems that we have today. So the statistical models are trained with examples, and those examples are represented by choices for features, and the estimators can generate likelihoods for what was said, and then the connection to artificial neural networks, or ANNs, I guess I kind of use interchangeably in this talk ANNs and MLPs, they can either generate features or they can generate likelihoods. So in the first wave of neural nets being applied to speech, we had something based on McCulloch-Pitts' neuron model, which I'll mention briefly, and then people were using what was called the perceptron learning algorithm, other work with Adlines, and I'll go into each of these a tiny bit, and something that was called discriminative analysis iterative design, which is far less well known than the others, although it was actually widely used for applications. So the McCulloch-Pitts model is basically modeling the firing of neurons by having some weighted inputs summed up and then seeing if the sum exceeds some threshold, and then the neuron fires. the perceptron algorithm is making use of this kind of picture to try to figure out how to train the weights. The difference between perceptron and Adline learning is basically that perceptron learning is adjusted using the outputs, whether the neuron fired or not, and Adline is adjusted using the weighted sum before that threshold. And the initial versions were a single layer. And in 1969, there was a book published by Minsky and Papert about perceptrons, which had a pretty negative effect on development in this area. They pointed out, among other things, that a single perceptron could not compute an exclusive OR. But interestingly, 8 years before, that same lab in Cornell that was being described in that book actually developed multilayer systems. An example of this was discriminative analysis iterative design. So how did this work? There were Gaussians at the input layer and perceptron at the output layer. And the perceptron was trained by gradient training. And that gradient training was using an exponential loss function at the output. The first layer, hidden layer, was very much like radio basis functions that were later developed. The input patterns contributed to the Gaussian training of the Gaussians, but they were weighted based on the distance from the targets using this exponential loss function. So this was actually pretty sophisticated. It was multi-layer. It was not homogeneous layers like we tend to use now, but it worked pretty well. It actually had built into it some feature selection as well. It looked at different combinations of input features. And it worked on a number of things. It was used by NASA. It was used by McConnell Douglas for commercial applications. It was actually pretty broadly used, but it wasn't very widely discussed in academic circles. And it actually wasn't used for speech. So I only mention it just to respond to this notion that a lot of people have that we didn't have multi-layer systems until fairly recently. The Adline system, there was a 1963 Stanford technical report. This is a little obscure. I didn't know about it until Bernie Woodrow sent it to me. They did digit recognition with these Adlines, and basically they had Adlines that looked at all of these different frequency bands. That's what those each of these horizontal rows of boxes are intended to show. This, like the 1952 Bell Lab system, did work well within speaker. It didn't work much at all across speakers. Okay, moving on to wave 2. These were homogeneous multi-layer perceptrons. And the reason I call them homogeneous, again, is because each layer pretty much looks the same. It's a bunch of differentiable saturation functions that the weighted sums feed into. There were some earlier non-homogeneous systems that led into this wave. I actually claim a little bit of credit. We did some voiced-unvoiced stuff at National. It wasn't full speech recognition. This was in the early 80s using some of these things. Mikino and colleagues did consonant recognition fairly early in the 80s. Some of the more homogeneous systems, Weivel and Hinton for stop consonants in the later 80s, and many others built things largely for isolated word recognition or phoneme recognition or particular classes of sounds. And then by the late 80s, full speech recognition. So a number of us started really moving forward pretty quickly on large vocabulary continuous speech recognition starting in 1988. So Herv Bourlard and I worked with feed-forward networks, as did a number of others during this period. Recurrent networks were the focus at Cambridge University with Tony Robinson and Frank Fallside. In the case of both approaches, what you did was you trained these nets to generate phone posteriors, and then you divide by priors to get scaled versions of the emission likelihoods for hidden Markov models. And we called this the hybrid HMM MLP or HMM ANN system. Now, just as quick point of looking ahead, many of the systems that operate now with more layers that people call deep networks use exactly this method for doing speech recognition. So speech with MLPs use... oh, question? Sure.
Yeah, just a quick question about the recurrent system in 1990.
Yeah.
I'm surprised at how early that was, given that training of recurrent networks only really showed up around 89 or 90 with Williams and Zitzer and with Jeff Hellman.
Yeah.
And they were doing much simpler kinds of networks than a speech network.
Yeah. Oh yeah, no, I mean we were involved in DARPA competitions together actually, and the recurrent nets worked about as well as our MLPs. They also used fewer parameters, and so they were faster to run. The negative thing about them is they weren't any faster to train. They sort of did an unfolding in time, and they were a bear to get stable. And so there was a period of time, I'm sure this isn't true anymore, there was a period of time where the only way anyone would be any good at doing this would be if they were a student or colleague of Tony Robinson's. And so we didn't use them in Berkeley because I wasn't Tony Robinson. And it was just, it had stability issues, which you never had with the feed forward. So I thought if I ever was involved in a startup, I probably would have used it because it uses so few parameters to get the same result. And once you have it trained, it's great. But training for students, I thought it was, they could step right into the feed forward and get going the next day. But yeah, no, it was, they were quite competitive in a number of evaluations in the early to mid 90s.
If someone's citing recurrent nets, should they be citing this in preference to Ellis?
For speech recognition, yes. Yeah, I mean, recurrent people have done lots of things for lots of tasks, but for speech recognition, yeah, I would cite that. The later ones from Robinson, after Frank passed, had much better results and so on, but this is sort of a core initial paper for using it for speech recognition. I want to go forward. Okay, so speech with multilayer perceptrons, it's basically the same as other tasks with multilayer perceptrons. You're using the chain rule. There were back in the 80s, there were lots of arguments about who came up with error back propagations. People were sometimes crediting Hinton and gang, and then others were saying, no, Verbos did this in his thesis. When Bourlard and I did our book, we decided to go past that, and we cited Newton. And then Jan LeCun took me to task for it and says, oh no, it was Lagrange. But anyway, I thought Leibniz maybe. But anyway, so it's a chain rule. And so you have simple use, powerful transformations. You can use these for classification, for prediction. We were primarily using it for probability estimation. And initially we were using it for a limited number of classes. This was for monophones. So when we did, as actually Hynek was reminding me this morning, when we did head-to-head comparisons at the time with Gaussian mixture systems and earlier with discrete HMM VQ systems, for monophone systems we were pretty much always somewhat better. But for context dependent, it was a little tough. So in principle, you could have a posterior probability of a state Q given an input X for any number of classes or states. But practically speaking, with a few hours of training that we had and the limited computation, even though we went to the extent back then of actually designing and building our own VLSI to do fast computing, even with that, there were sort of limitations of what we can do. And so,
and the song.
Well, yeah. So, because of these practical considerations, we were looking for different ways than just straightforwardly having lots and lots of outputs. And so we did a factorization. So the probability of Q and C is a context, particular context, given X, given the input features, it can be divided up in a couple ways with no assumptions. So the expression that you're seeing there has no independence assumptions. So if you look at the first one, it's saying for each assumption of context and the input, what's the probability distribution that you get at the output, and then you weight that by the probability of that particular context. And you can also go the other way, where you end up with a slightly stranger one, but multiplied by the monophone probability. So we did experiments with this. We also worked with SRI, who developed some nice smoothing methods, and we actually got some pretty good results. But we did this with sort of limited context, the sort of general classes on the left and the right. We got nice improvements, but it was enough more of a pain that honestly we never got into using it in a big way. Actually, somewhat later, in the later 90s, a couple guys at CMU worked with, actually got up to really a lot of context with many, many triphone classes. And they did this using a tree of factored MLPs. So you could think of this as being incredibly deep, because it was this whole big tree, and you'd go through each of the MLPs to get to the next one. And that one was quite competitive. It actually worked comparably to the best systems at the time. The problem was it wasn't any simpler. It was actually a big mess to train. Took lots of effort to train. It wasn't better, and it certainly wasn't simpler than the other systems at the time. So it never really caught on. But again, if someone thinks that, oh, people didn't do any work with context-dependent multilayer perceptrons until the last few years, it's just not true. So the limitations for artificial neural net automatic speech recognition by 2000, the Gaussian mixture approaches had matured. People had developed many refinements, MLLR, there were discriminative approaches. I don't know, is Dan here by any chance? Yeah. Over there, yeah, okay, you're right. So MPE and all sorts of cool things were developed for these Gaussian mixture systems. I mean, Gaussians have some nice properties. You've got your means, you've got your variances. There's all sorts of nice things you can do with them. So people developed all this stuff, and you had many people at many institutions working really hard, doing all sorts of interesting things. And we still found that, although we found that our approaches were at best equivalent, everybody else was doing something different. And we still wanted to use multilayer perceptrons for experiments with different front ends. So the question was, how could we take advantage of both? Enter, actually, Tina Kromansky, who was working with us quite a bit at the time, along with another great colleague, Dan Ellis. At this time, we were working on a competition for front ends done by the European Telecommunication Standards Institute. It was called the Aurora Competition. You've probably heard of the Aurora database, those of you who work in speech, and a lot of Aurora tests people have done. But this was initially a very specific competition to come up with the best front end for what they call distributed speech recognition, where you computed a front end at the cell phone, and then somewhere else they would actually do the rest of the job. So for this task, they thought of them as decoupled, which I think is wrong. I think that you sort of have to consider the whole thing. But they thought of it as decoupled, and so the models were required to be Gaussian mixture-based hidden Markov models. We found the MLPs to be useful, so how are we going to use them and fit into this? So Hermansky et al. Came up with this idea to use the output as features, not as probabilities. So the resulting advantage is we can connect into complex hidden Markov model GMM systems. Now, I can't claim this for myself at all. What I really got jazzed by was that on a sort of management or sort of social level, this meant that we could interact with many more places. It meant that we could connect to someone, we could connect to CMU, BBN, SRI, and we could just say, oh, we have some nice features for you. And then they would say, oh, we'll try them out. And if the features helped them, then that was good. We didn't have to sell them on our whole philosophy of using neural nets for speech recognition. So that was more amenable to collaboration. Now, to be fair, this was not the only time that people had used neural nets for features. People at SRI, or Heck and Yochai Koenig had done things with speaker recognition where they had used output as features. Renato De Mori reminded me of some things that they had done prior to that with neural nets outputs as features. But this was a systematic approach to using it, and it's actually gained a lot of use. So I think the people who are not using neural nets to generate emission probabilities are using neural nets to generate features, either from the output or sometimes from somewhere earlier, and that largely came out of this work. There are a number of variants of this. Under Hennick's group, they developed approach using networks that were trained in a constrained manner, so that they were constrained to learn temporal patterns in individual parts of the spectrum, and then you combine them in some way. We had our own version of that in Berkeley, where we trained up something on these individual critical bands, and then we only use the input to hidden transformation. We then pasted that input to hidden transformation into another set of nets, which is basically, again, the approach that people are using in many cases when they're not using the hint and pre-training. They're actually doing discriminant training, taking a piece from that and doing. So this was work by Barry Chen, who was a student of mine there. And then a number of approaches where people are looking at temporal or spectral modulations, such as MRASTA or Gabor features. And then something that's been quite popular in the last few years is bottleneck tandem features. That is where instead of taking the output and doing something with it, you take something earlier on, and typically a constrained layer. And the main positive thing about that is that you can have different nets for, say, different languages with different number of phones and so on, and you can keep the dimensionality the same, which has some convenience. Okay, so about the third wave, redux. I like this Harry Truman quote: "The only thing new in the world is the history you don't know." So there's a lot of history people don't know. It doesn't mean you can't do something new, actually, but. Okay, so there's actually nothing wrong with the original hybrid theory. By hybrid theory, again, I'm referring to the hybrid of neural nets and HMMs, where you get probabilities, likelihoods from the neural nets. Practical considerations led to the earlier victory for GMM approaches. The fact that it is more straightforward to do these very, very, very context-dependent systems with Gaussian mixtures. So the fundamental issues were how to apply many parameters usefully and how to get these emission probabilities for many phonetic categories. But parts of the solution are already there. So applying many parameters, well, traps, hats, and other efforts did already show how to generate MLPs layer by layer. Many phonetic categories, well, if you have a lot of data and you have enough computation, you can do that. Learning approaches, that is, how can you benefit from many, many parameters? There were second-order methods and various forms of regularization that people were experimenting with in the 80s and really got very far in the 90s. But someone had to do this. And, to be fair, people weren't doing this until in the last 6 years or so. So what's, I think, most important about this revival is that people are doing it. So this may have started with Jeff Hinton getting excited. So he's very excitable. Good guy. I like him. And his excitement is very contagious. He's very smart. He's very good at explaining what he does. And he developed some particular initialization techniques. Now, he's actually been interested in Boltzmann machines for a long time. But he and his students developed some nice way to use restricted Boltzmann machines, which I'm not going to get into. But it's basically an unsupervised learning technique which allows you to set the parameters, set the weights of the neural net to some good initial point. Now, they tend to refer to that as the main deal, and they refer to I don't know how to, there we go. Yeah, because it's not showing up my screen. Okay, I got it. This unsupervised technique allows you to set the weights into a reasonable place, which I think is a good point. They refer to the error backpropagation part, discriminant part, as being fine-tuning, which I find kind of funny because without that you won't be able to classify anything. But anyway, it permits the use of lots of parameters. I had an email exchange with him at one point where he was, I was saying, well, you need a lot of, you have a lot of parameters for the amount of data, and he was sort of saying that's sort of the point, that in fact you can get useful information out of many, you can usefully set many parameters, even though you don't have quite as much data as you might like. So he talked the guys at Microsoft into working on this, and they got excited about that when they got some good results. They started off with timid kinds of things. They went to large vocabulary ASR, and they got some good results. People at Google and IBM got curious about it. They tried it, and everybody wrote lots of papers, and everyone got excited. So initialization is, having a decent initialization is actually not, the general idea at least, is not particularly new. Back 25 years ago, when we were starting a new task, we sometimes would take the weights that we had from working on some other task and start off there so that it was somewhere reasonable. We had sometimes used it for transformation to new languages. We had nets that we used in tandem mode in a large project where we trained them on English, and then we were going to Arabic, so we started off with the ones we had from English. So having a good initialization can be very helpful when you have insufficient data for the new task. Yes?
I think you're going in the direction. I have a question on really this question of initialization. What does it mean?
Yeah.
Does it really mean that you, in the training process, I think you're going in a different direction. Note what I'm going to say.
Okay.
I think what Ethan is trying to say is that in the training process, let's not use something uniform all over, Markov or whatever, but use maybe a much more sophisticated learning, maybe something based learning. Initialize the machine, and then you can go and do backpropagation to fine-tune, the parameters. So it's really about the inhomogeneity of the learning process rather than whether you just take another system type of parameters.
Well, yeah, I'm saying that having initial values for the parameters can be very important. But there's different ways that people have done this, and for different purposes, right? And I mean, in particular, I can't remember if I say this here. One of the things when you do backpropagation, if you have quite a few layers, is that the layers that are far from the targets change very little. And so they're going to be very close to what you initially set them for, and if they're going to be useful at all. And so the argument, which I think is reasonable, that of why in the older stuff we didn't get much advantage out of more than a couple hidden layers was because eventually the training isn't even affecting those early layers, right? But the unsupervised learning approach he does is only one of the ways that people, even now, in fact, it's not dominant anymore. Most of the big places are actually doing discriminant training sort of layer by layer. And that works just as well. And so I think my point was just that having some good initial point has been known for a while to be a good thing. But yeah, he certainly was coming from a different.
The point what you made is that without backpropagation, the net wouldn't work.
Yeah, it doesn't. It's the reason I objected to be called fine-tuning is that if you don't do the good initialization, you'll still be able to do some classification. Whereas if you don't do the so-called fine-tuning, you will not, because these things are set to something inherent about the data, and it doesn't know anything about versus or anything like that. And I actually asked the student to do that, even though he thought it was a silly exercise, because of course it wouldn't do anything, and of course it doesn't do anything. Yeah, it's sort of a random result. Yeah. Yeah. No. I'm saying that the technique a lot of people are using is to build it up layer by layer. So then once you get to the second or third one, the initialization is what you found with the first layer and so on.
Meaning that every layer is trained as if it were the final layer.
Yes.
And then you either freeze it or not.
Yes.
This is really cascade correlation, right? From, I think this idea goes back to 1986.
Yeah, you could say it's related, right? But the details are different, clearly, right? But, yeah. Yeah.
So when you said you had somebody, and obviously if you don't have a supervised layer at the end, you're not going to hit phone targets.
Right.
But if you were to do some kind of clustering task, would
Yeah.
the clustering work better on the output of the unsupervised bit than it would have on the original feature?
Not sure I understand the question.
The idea is if you just wanted to take the output after pre-training
Yeah.
and do some clustering and then hope that you get something like phonemes, do you think you'd have a better shot at that than you would have if you just tried to do the clustering on the input?
No. No, I think that if your task is, if you have supervisor information and you're trying to distinguish between particular classes, there's really not much substitute for actually making use of that information. It's.
Well, no, so I'm saying if you didn't have it, would you be better off having done this unsupervised pre-training procedure?
If you didn't have any supervisor information,
Right.
you're not going to do speech recognition then. There's other things you could do. Yeah, other tasks I'm not going to make a statement about. Okay.
No, but Morgan, I think Aaron's point is a little more, not subtle, a little more assertive than what you made now.
Okay.
He's saying, or he's proposing, he's not claiming this to be
Yeah.
true, I think, or at least I'm proposing it now.
Okay.
That what the pre-training could be doing
Yeah.
is creating these 30 or 50 or whatever number of phoneme or allophone categories.
Yes.
It just doesn't know what to call what.
Yes.
And all the fine-tuning is doing is giving these clusters names.
Yeah, I don't believe that.
That was the basic
Yeah,
thing.
yeah,
That's true.
I don't believe that.
Well, then it would work, right? In the headset.
Yeah.
Because the teacher is tracking and he does.
Yeah. Anyway, let me move along because I still have a fair amount to do. Sorry, but I'm happy to try to answer the questions. Let's see, where was I? So, right, this approach was applied to lots of things, not just speech. Gave reasonable weights, and later speech work, as I say, sort of skipped this step and instead did the layer-by-layer discriminative training, and use some kind of regularization to avoid overfitting. Recent MLP work, people are showing a fair amount of improvement over comparable GMMs, usually in hybrid mode, that is probabilities for the HMM. And they've also, probably the biggest success has been to give it another name, which is call them deep neural nets, although they're still, multilayer perceptrons. So here's a question for some that I think we've got a little bit of insight into in some recent experiments. How deep do they need to be? How deep should deep be? Okay, so many experiments show continued improvement with more layers, with some diminishing returns after, say, 7 or so in a lot of these large vocabulary experiments. But the underlying assumption is that there's no limit on parameters. So we were asking, what if we did put a limit? It's not a dumb thing to do to put a limit on it because there are practical considerations or time and storage, for running these things and training these things and so on. And you could think of the number of parameters as being a not completely unreasonable proxy for resources in general. So Oriol Vignoles, who's been working with me, did this work that we reported at Interspeech this year, which we call deep on a budget. So you have a fixed but very large number of parameters. It was quite large. It was more than the number of examples that we were training on. And the old rule, which used to call Uncle Bernie's rule, Bernie Woodrow came up with, was that you're supposed to have 10 patterns for every parameter that you're learning. It's a little outdated because there are these regularization techniques and so forth, and you can actually do better than that. But anyway, so this is common now in these deep nets for speech. They commonly have more parameters than they have patterns. Yeah, and it's partly because they have some nice initializations, partly because of nice regularization techniques and so on. But anyway, let's say we have. I just was concerned that people wouldn't say, "Oh, you used too few parameters." So we have a large number of parameters, but it's fixed. And so that means as you change the number of layers, you're varying between narrow and deep versus wide and shallow. Now, there have been quite a number of experiments that people reported before this where they compared one really huge hidden layer with a deep net. And they always come out that the deep net is better. But what I was thinking is, okay, it's good that they kept the number of parameters the same, but let's look at all the steps in between. How about with 2 layers? How about with 3 layers? And so on. So what works best? And we did this with a data set where people commonly vary the signal-to-noise ratio, which is the Aurora 2 data. Lots of limitations to this data set, so I don't want to make too broad a claim for data sets in general. But anyway, this is digits with additive noise from train stations and speech babble and lots of other sources. Many people have worked on this. So we have a fixed but large number of parameters and clean training. So we're looking at the mismatched, not the multi-style training case. And what is best? Well, it turns out that for some signal-noise ratios, 7 is best. But for most practical signal-noise ratios, 10 dB or better, 2 is best. By practical, what I mean is if you're getting 4 or 5% error on digits, that's bad enough. That, that's probably as bad as you can deal with, even with some other constraints. Worse signal-noise ratio than 10 dB, people get really quite terrible numbers. So for most practical signal-noise ratios, 2 is best. And then we said, well, what about maybe we just picked some very particular point in the number of parameters, so we'll try with half the number of parameters and twice the number of parameters. And we got qualitatively similar results. So a hypothesis is that how many layers you should have, if you have this constraint, might be task dependent. So here's a picture of showing what the best number of hidden layers were for different signal-noise ratios. It varied between 2 and 7. But if you look at the last bar on here, this is the average over all of the signal-to-noise ratios that are 10 dB signal-noise ratio or better, which I'm calling the usable amount, again, because of the kind of error rates that you get. And 2 is actually best in this case, not 7, not 6. To give you an idea about the word error rates, this picture is varying between 3.8 at the bottom to 5% at the top. And the best number is something like 4.3%, a little under 4.3 for two hidden layers. And I think because of the small differences that I'm showing here and the size of the task, I wouldn't make any grandiose claims about this, saying you must always use 2 or something like that. But what I would say is you don't really get any benefit from going to more. And that is, again, with this constraint of having the same number of parameters. So, so that's a good stopping point for the question, yeah.
Yeah, I'm wondering, the bumminess of the graph is a little puzzling. Is there only one network in the case, or did you average a lot of random restarts?
This is just one network. It's true. Yeah. So no, you're right that we could improve that by trying a lot of different starts. But I think the point of this was not so much to say this is the one you should use, but to say you should exercise caution in thinking, yeah, that's really more the point. Yeah. No, you're right. You get better analysis if you did that. Okay. Now, another thing about this third wave is that I would say that true believers think that the features aren't important. It doesn't matter what you feed it. Machine learning is wonderful. It will learn everything. This is demonstrably not correct. It's an example of garbage in, garbage out. People have done experiments on small tasks with waveforms. Back in the day, we did this and got some pretty terrible results, and I have to say that the people doing this now are getting better results than we did with waveforms. That's great. But they are still worse than fairly simple features, MFCCs. Yeah, just this speech time series from a microphone. I mean, you could argue, as friend Hinek has pointed out to me, that isn't necessarily the original either. That there's the issues of what you're capturing with a particular microphone and only one microphone and so on. But anyway, taking that as a given that you get the waveform, they still don't do as well as you do with features. But you might say that was quibbling because it's kind of amazing if you get 23% phone error rate on Timmit. The best results are maybe 19% or something. So that's exciting. We used to get more like 60% error rate trying out the waveform with our techniques. However, it's not really true because if you read, so I'm thinking in particular of a paper from Hinton's lab in 2011 where they did Timmit phone recognition from the waveform. If you read the paper, they actually took the absolute value, they floored it, they took the log, they averaged over a number of time delays. And so they did one thing after another that basically obscured the phase, which is one of the key things that happens when you take the power spectrum. The logarithm turns out to be kind of a hard thing for the system to learn, which seems like it wouldn't, but actually the automatic systems are not learning the logarithm without you taking it. If you take a deep net and look at the power spectrum, then you take a deep net and look at the log power spectrum, you actually do significantly better. So the features do kind of matter. There was some more recent work this year, I think from IDEAP, where they proceeded from the waveform and they were using convolutional nets, and they also did reasonably well. But they were doing max-style pooling of the convolutional nets, and this also obscured some of the phase effects. So I think doing something at the feature level is important. And when you start looking at mismatch cases and all the many results that people have of interesting ideas that people have for how to combat the problems of mismatched acoustics, MFCCs isn't even the right comparison point. I mean, MFCCs are pretty poor compared with a lot of the features people do. So I think this is just wrong. And so the purpose of the front end is to improve ASR by, quoting my colleague Hina Kermansky, to destroy information. Because some of the... I was being vague and you're being more specific. That's right. Some of the, you want to destroy the information that's misleading. So you got to read the next bullet, Scenic. So the information that's misleading, the information that's ineffective, you want to focus on the discriminative information for whatever your task is. The waveform isn't just language. The waveform has effects from noise, reverberation, channel effects, speaker characteristics, and so on. So if you had... it might be true that if you had the world's best statistical model, that you could have a really trivial front end. That could be true. But it's also true that if you had the most amazing front end in the world, you probably could do pretty simple recognition. So I think the deep nets are very nice. I'm really happy that they're moving forward. It's stuff that we've been interested in for a long time. But the front, what you feed them still matters.
That doesn't mean that you cannot find a language for the waveforms.
Yeah?
Waveforms no language.
What I mean is that it is not only, the waveform is not just a byproduct of what the person is saying. They're also a byproduct of other things in the acoustic environment. It's sound. Right. It's
I mean, I guess you're looking on temporal processing, and I'm just saying that, it's just...
I'm saying that because it isn't just the information, Hynek was saying bad information. It doesn't just have the good information, it has bad information in it too. And so, yes, you could imagine having a model that...
We have to be careful generalizing in kind of, I don't think it's all skills, because you'll go and say, well, tomorrow, doesn't say, well, we shouldn't really do this.
What is it that I'm saying we shouldn't do?
I think, the argument that you cannot work with the waveform is kind of...
Oh, I'm not saying that.
Okay, so that is really the point.
No, I'm not saying that. What I'm saying is... Okay, I'm saying is that it's probably pretty hard because there are things that you can do that are pretty straightforward. That
universities to do hard things.
Yeah, that one's really hard. I think it's, and I actually, yeah. So I would actually say it's, it's my opinion. I think it's a bad idea. Okay? Because I think that you ignore the fact that you can do a lot with processing the waveform. That is very helpful, and it's demonstrably the case. So I could be wrong. I like it when people show me that I'm wrong. I mean, not just guess that I'm wrong, but show me that I'm wrong, because then I learn something. But I have opinions as I go along, and my current opinion is that doing something with the waveform that makes sense is a good idea. Just briefly, Jack, we need to move along. But
Well, there's something to do with the word signal for waveform.
Yeah. No, I don't think he's happy. Yeah. Yeah, no, I'm saying the signal that you receive, that you're working with, you digitize it, you got a bunch of numbers. That number reflects a number of things that came into it, and not just the speech sounds. And so, if you have something simple that can take care of it, or partly take care of it, it's a great benefit. Yeah.
I can save this question for the end if you have a lot more to go.
So we have till 1:15 or 1.
More like a little after 1.
A little after. I should move forward then. Okay, and we can talk separately if we need be. Okay, so why use MLPs from the perspective of front ends, which is that they have few distributional assumptions. They can easily integrate information over time. You can incorporate parameters in more ways than just by adding layers. You can actually incorporate them by having multiple feature streams. You can have quite a few parameters that can be used quite effectively. The outputs can be posteriors, and even if you're not using them as posteriors, if you have multiple streams, the fact that you know their posterior probabilities makes them much more easy to combine. And if used with a deep net, I like to think of them as deep and wide nets, so if you want another acronym, you can think of them as DAWNs. Early DAWN example was something that Barry Chen, a student of mine at the time, came up with, he called the tonotopic MLP, which was kind of like the hats and traps and so forth, but instead of training them separately, he trained it all at once. And this kind of worked reasonably. You could think of it as a deep net with some constraints at the beginning. Something that has been done with some of Hennick's colleagues, and also that we've been doing, is splitting up by temporal modulations. You can have high temporal modulation filter bank and a low temporal modulation filter bank, and combine with different nets that have some degree of depth. Lately, we've been using sparse PCA to do feature selection, so you don't use all of the different modulations. And for this particular task, we're using bottleneck approaches. So how neural are these things? So nearly all of these are based sort of distantly, at least, on the McCulloch-Pitts model. There are some people who've done some work with more complex units, and sometimes they seem to show things are a little better, but there seems to me to be a lot of complexity and only a little bit of improvement. So if you have either width as in multiple streams, or depth as more layers, this adds more complexity and adds more power to the representation. Another point that Nick and I have liked for a while is signal correlations that are represented by length. But still, the most effective learning methods are not biologically plausible. And is there a way that we can still benefit further from biological models? So first off, what can hearing do that ASR can't? Well, we have stable perception in moderate amounts of noise and reverberation. We have the cocktail party effect, which is you can hear one voice out of many. You have rapid adjustment to changing conditions. And you have pretty much real speaker independence. So how can we learn from the brain? This is just something that I'm excited about recently, so I'll just tout it for a couple minutes. There are new sensor capabilities that permit direct cortical measurements, ECOG. Basically, this is a bunch of sensors placed right on the surface of the cortex for surgery patients. It actually has a clinical purpose, but while they're there, you can read them timid sentences and so on. And this is giving new clues about source separation and noise robustness, and I think we can learn something from that. So the hope is that measurements like this can lead to new processing steps. We can take this system that works pretty well and try and get some other hints of what to do. The processing steps can suggest new structures. I think it might not just be a question of adding on sort of homogeneous same size layer after layer after layer, but maybe there's some structure that's suggested by it, much as we had some interesting results from the structure of separating out the low and high tempo modulations. Having some combination of signal and computational levels, I mean, in the end, you build a system that has models and it has feature processing. And all of it works together, and you probably have to think of the whole thing eventually, even though for our research we tend to focus on one part or another. In particular, understanding the statistical systems can show the limitations. I don't have time to go into it now, but we recently did a study where we found for relatively matched conditions, if you can match the assumption of conditional independence of the data through some resampling techniques, you can get rid of nearly all of the errors in large vocabulary speech recognition. It's an artificial case. It's not something that we then can apply to what you would do in a system. But diagnostically, it shows that there's a huge number of errors coming from that. And for a mismatch case, it's the invariance of the front end that you can show. There's many different waveforms, for particular speech sounds under many conditions. But if you can have an invariant front end, you actually, in principle, could get rid of the rest of the errors that show up. So you need feature stability. You need features that are more stable under different kinds of acoustic conditions. And you need models that can handle dependent variables. So getting up to the conclusions here, just a couple slides. Good. And maybe we'll have a few minutes for questions. So using artificial neural nets, multilayer perceptrons in particular, for speech recognition, it's really 50 years of efforts. The current methods include Tandem. As a subset of that, there's Bottleneck systems and hybrid system where you use the output of the nets as probabilities. Multiple layers do sometimes help. If you have a fixed number of parameters, you might see whether it actually helps to add lots of layers. But I think going back to that point, I think the main point I wanted to make is when you're doing, this is just a methodological point, when you're comparing two systems, to start with, use the same number of parameters for the two systems. This is kind of a basic thing. But initialization often helps. As with speech recognition, the fundamental algorithms are quite old. The basic hidden Markov model algorithms are over 40 years old, and the basic multi-layer perceptron algorithms are not that old, but pretty old. The engineering efforts have helped, and so has Moore's law. Last bunch of years, although Moore's law continued with many, many transistors, the clock rates have not gone up so much. So the main improvements that we get are from having lots and lots of parallelism. These things are massively parallel, so as long as you have good communication between your arithmetic units, you can benefit a lot. The features still matter. Maybe sometime we'll develop such clever modeling and machine learning techniques that the features won't matter. But at the moment, at least they do. And deep is not the only game in town. There's also wide. And what's the missing tenth that Watson didn't notice? Well, speech recognition still performs badly for conditions unseen during training. So we still need to look hard to find the tenth. And that's, as you pointed out, that's really for the younger people here to actually find. And if you find it by striving to prove some of the things I've said wrong, that's great.
Usually it's the
Okay. That's it.
I guess we have a few minutes?
Yes, yes,
Okay. There's a lot asked during the talk, but not mostly by old guys, so. Okay.
So it seems like, with Babel, for example, that a lot of the gains that people are seeing from the deep net stuff disappear when you have like 10 hours only of training data or something like that. I mean, do you think that these things are just a sort of graceful way of absorbing more training data, or that there's some story that's going to allow this technology to be as successful as it's been lately on tasks where you don't have as much training data?
It probably depends on the task. So, I mean, we had, comparatively little training data with Aurora 2, and again, for the noisier case, it still helped quite a bit to have more layers. But I think that the biggest jump, and you have to take this with a grain of salt because none of these jumps were super large, was between 1 layer and 2. So I think that going to a second hidden layer is probably a good idea. Maybe the initial is, in fact, in that case, the initial is we were using restricted, I didn't mention this, we were using restricted Boltzmann machine pre-training, and it had almost no effect with 2 different layers, which I think people have seen. It's when you have many different layers, it's when you see the biggest effect. So with a small amount of training data, yeah, you might find that going very, very deep doesn't help you so much. But if it's a task that's very difficult, you might find that some width might help. If the width, it's not just width, maybe something I wasn't clear about. It's looking at the signal in a bunch of different ways. And so if you can look at the signal in a bunch of different ways and have some reasonable way of telling the system which ones you should emphasize, I think that can be very helpful. Yes, sir.
So the vision community, there is an undercurrent, mostly by very well-known, driven by a few people that are really fantastic statisticians, that they are really anti-statistical, like Stu Gimmer came and gave a talk about. Really, statistics, all these abstract models and big group of networks and whatever, without really building knowledge in the system, doesn't take us anywhere.
Knowledge like geometry?
Yeah, geometry, knowledge, yeah. Physics in this case, yeah, exactly. That's what I meant.
Yeah.
So, is there an analogous, do you envision an analogous undercurrent here where we're going to go more towards more physical models, production and whatnot, or you really think that doesn't really matter?
Well, there are people who are very interested in physical models for production of speech. I think that kind of makes sense with a generative kind of system. If you're talking about a discriminative system, I think it's more interesting to look at perception. So that's why this is where I think and I are unified, that we want to look at how, what's the process for actually perceiving speech. And if you can have a model, a physical model of that, it can be very good. Now, one of the things that is tricky about that is that the human hearing mechanism is there for many things other than recognizing speech. It was there a long time before. And so, you could, years ago, a fellow came to Berkeley from Caltech who was working in Carver's Needs Group before that, named John Lazaro, and he built a bunch of very clever chips using sub-threshold MOS that put out all sorts of interesting things that they measured in auditory systems of animals. And the results were very noisy, but they thought, well, that's fine, because things are noisy in the brain too. And then he tried feeding these things into HTK, and the results were terrible. We were happy because he plugged into a neural net system and was much less judgmental about the nature of the features it fed in, so it did much better. But with these chips, he never got any better than MFCC.
But why is it relevant? I thought my comment was more about the HMMs and the GMMs on the front end. Because if you were,
I misunderstood.
Yeah, because it's not really. It's where you in a sense the HMM it's it's your hypothesis generating machine, but it's a very trivial or a very tractable and all that. So that okay, yes, I guess.
Okay, so let me try to answer that one instead.
Yeah.
I didn't understand the question.
So yeah.
So I think the model, if you're using statistics, which I think is one place to start. If you're not using statistics, I don't know where you go. But if you're using a statistical model, then the core question is what is the nature of the statistical dependencies between different things in the model?
Yes.
And so, for instance, people, Jeff Bill, that's right, this GMPK, which is a graphical model toolkit which allows you to put in just about any dependency anywhere. But the problem with it is that then you don't know where to put them. And so I think, yes, changing that model in such a way that it reflects the nature of the signal that's received, the dependencies in it. As I said briefly in that one experiment, we found that at least under match conditions where you don't have the problem of the representation not being invariant to different acoustics, in that case you get rid of essentially all of the errors when you screw up the data in such a way that it matches the assumptions. So this at least implies that if you change the model in such a way that it better reflected the actual dependencies in the signal, you go a long way towards improvement.
And the generation, the machine that generated the signal that you're actually the environment.
Yeah, sure. Yeah.
So when you're talking about the importance of features, you mentioned that, say, log is kind of surprisingly hard to learn.
Yeah.
I guess this is a local optimum thing. Can you elaborate or speculate a little bit more on why? Like, is it because of the particular artifact, the way that you tend to initialize things, or?
I really don't know. It's just an example that people have seen that they end up doing one sort of little thing after another in order to get up to reasonable performance when they are proceeding from the waveform. And so the logarithm turns out to be important. But that's, when someone publishes a paper, they also, they tell you a certain amount, but they're maybe not telling you exactly everything that's in the code. And so and we haven't experimented with that ourselves, so I don't know. Right? Yeah.
I wanted to actually also maybe step into discussion which was here about providing some more physical insight into the process. I think that since we talk about neural networks, those are very convenient mechanisms for doing so, because you can make all kinds of structures, right? You mentioned Barry Chan's model where you would put a separate classifier at each frequency, and then you have one more which was using the thing. It's very similar to what Tandem was doing. Barry was doing it all in one thing, but he provides the structure which makes sense.
Yeah. You mean more general graphical models, more general. It doesn't have to be neural networks. Right?
No, but since we are at neural networks, I just wanted to point out that this is a very convenient mechanism for doing so. Because you can do things like you have one stream which takes low modulation frequencies, one stream which takes high modulation frequencies. You can combine them in various ways, which of course come from the knowledge what we sort of observe in a perception. So that's not very good for this.
No, so I think clearly structure can be built in that way, but I think what he's referring to is, in all of these cases, at least presently, we feed into an underlying statistical model, which currently is a hidden Markov model, right? And the question is, does that matter? And I think it does, even though I like to play around with the front end, but it's nonetheless true that again, when you resample the data in a clever way, so that you get rid of the mismatch between the conditional independence assumptions of the model and what's really there in the data. For the match case, acoustics case anyway, you get rid of essentially all of the errors. So that suggests that model as well needs to be different. Yes?
So for these deep neural nets in this kind of black boxes, you can argue about whether black boxes became a bad thing, but you might still wonder, do we have something to learn from these black boxes? And how much, have you done any analysis of what these nets are learning, the structures that form in them, and maybe things that we could improve on by learning what's going on inside the black box?
So, I haven't. But let me tell you just an older example where we did. In Berichen's tonotopic, no, sorry, this wasn't the tonotopic method. This was, he trained it now wouldn't be considered deep at the time for us, we thought it was two hidden layers. And looking at the whole time frequency plane. And what he found was that when he had sufficient data, he ended up with patterns that were very similar to what he was getting with the traps and hats and so forth. So it does seem like there is, when you do these things, it's likely that you'll get some kind of patterns at the start, at least, that are sort of sensible. And so there have been some work in that. I think Enoch has some other experiences with this as well. When you're talking about something that's 6, 7 layers deep, I think that's going to be really hard to figure out.
So here is the professor speaking to students, right? There is many techniques for analyzing nonlinear systems, especially in biology, and engineers tend to ignore them. Just a very simple things, reverse correlations or various stuff like that. I would encourage students to look what biologists are doing when they are trying to figure out what the nonlinear system, such as human perception, is doing. And they are coming with surprisingly enough conclusions. You don't do it too much.
Yeah.
And I don't know how to do it well either because I'm not a biologist. But if I were a student and were interested in questions like you are asking, there may be a means. Basically, you just say, oh, this is all black box and it's non-linear, please, let's push it away. Let's leave it for somebody else to do it. But
in all fairness, people have done it.
Things can be done.
Even in the workshop, what is the name? It's a she from SRI that she spent time here trying to analyze. Maybe SRI, a while back, you know. No.
I mean, Andreas is like.
Yes.
Liz Schreiber.
Liz, exactly, Liz. Yeah, I mean, she really, did a bit of that, trying to analyze the parameters and see where, what does it mean and what not.
Yeah, I mean, something we did back in the early 80s actually was we were looking at, again, nets that were less deep, but there we were very interested in what was the importance of the inputs and how it affected the outputs. And even though it's a nonlinear system along the way, you can do a sensitivity analysis and see how much a different input is affecting the output. And you could certainly do that for outputs along the way compared to how the output at the end of layer n affects the output of so that's, sensitivity analysis. Actually, we were doing that with brain waves at that time.
So we should.
Yeah.
Let's find out